So thank you again for the invitation to give this talk and opportunity given to share my thoughts about hybrid natural language processing, even in these times of deep learning era. Well, my name is Eric Laporte. I'm from Université Gustave Eiffel near Paris. And I will try in this talk to answer 3 questions. First, are we certain to resolve all the NLP problems with neural nets, or is it a risky bet? And then, if we are not sure that neural nets can do everything, what can they do? And what are good symbolic resources for NLP? How can we select the best ones? So let's begin with this notion of a bet on the future. Deep learning has achieved very important successes in translation and other applications. And this has created a lot of enthusiasm and an urge to explore the limits of deep learning, which is normal. But fans bet on a little more. They believe it will allow for doing NLP without any linguistic knowledge. This means that everything would be learned from examples by neural models. In particular, what we already know, or what we already know how to find out, would have to be learned by examples. Are they right to foresee this future? Are fans right to foresee this future? This bet comes from the idea that symbolic models don't work. Have we objective evidence that symbolic models don't work? And in particular, have we objective evidence in terms of precision and recall? I think it depends on the tasks. Let us take 2 tasks. The first one will be disambiguating phrases. For example, here we have a sentence with several occurrences of time. 3 of them means instants in time chronology. And the red one means a duration. So we have 2 senses and how to disambiguate each occurrence. I agree that neural models are better than symbolic models for this type of task. Now, let's take another task, which will be about place names, in particular unambiguous place names, and attaching fine-grained information to them, like in this text. Can you see my complete screen?
Yes, yes.
Okay, thank you. So in this small text, we have some place names like Enze, Chatsworth House, Hunting Tower, and so on, spotted, categorized, and we have the latitude and the longitude attached when they were unavailable. Okay, so for this task, I think it's obvious that a simple dictionary is better than supervised learning, since it's very simple with the simple dictionary with the right information in it, whereas a neural model would require huge annotated data to learn the same thing with the same coverage. So it's not so simple, as symbolic models simply don't work. Performance will depend on, in fact, on many things. What may performance depend on? As was shown in the preceding slide, it will depend on the content of added information, like the difference between disambiguation and spotting phrases. It will depend on the granularity, either fine-grained, like with longitude and latitude, or basic information, like is a phrase derogatory or laudatory. It will depend on which step in the processing chain, like if we have a processing chain with segmentation into, for example, tokens, detection of phrases and disambiguation. The performance can be different on each part of this chain, and it can also depend on languages. So it depends, performance will depend on many things. So comparing systematically symbolic and neural models would involve, in fact, varying all these parameters and varying them in all combinations. If we look at literature, actual comparisons, most of them are in competitions and shared tasks, and not in single studies. For a single study with comparison, it would mean that the author would be expert in both neural nets and symbolic approaches, and few of us have this both expertises. And so it's in fact in most in competitions where you can compare studies with a symbolic approach with studies on a neural net approach. And in fact, first, these competitions and shared tasks don't cover all the languages and all the type of granularity and so on. And in addition, they average out several types of annotation and several steps in the processing chain. So we don't have systematic comparisons. So literature does not tell us in what cases neural models are better and in what cases symbolic models are better. And this is presently, let alone in the future. So really, it's worth investigating what symbolic models are used for and what they can be used for. I'll skip some slides for lack of time. And to begin with, here two recent testimonies that symbolic models are being used in business presently. This choice of businesses to use symbolic approaches are based on the objective facts, certainly, because there are economic stakes. And I did, to prepare this talk, some reporter job about some businesses. And I discovered that Amazon's virtual assistant Alexa has a strong, efficient symbolic model, which has precedence over the neural model. That's to say, it is trusted by the assistant, which is not known, not widely known by the public. Google search also has symbolic component. You can guess that from the answers to some queries, but I saw a confirmation in a Google patent that uses language-specific predefined rules for matching and interpreting search queries. These predefined rules they call query patterns, like whether in place noun, and this is a symbolic resource. So, but the problem seems to be more that businesses don't find the resources they need. They are seeking symbolic resources. This is an ad from Colin of this year. Human-powered, an ad for human-powered quality data. I think that we can interpret this human-powered as data with symbolic information in it. And they are seeking professionals able to build such resources They are seeking methods to build them. Now, when they are faced with this kind of problem, whose responsibility is it to provide solutions? I think it's ours as academic researchers. I think the responsibility of academia towards business includes designing methods, providing and applying criteria of quality, training professionals, and in some cases, building resources. And what we are answering the businesses, if we all bet on neural models, is, oh, you don't need these resources anymore. Don't worry, you'll have cutting-edge techniques that do the same in a few months or in a few years. But how many years? And now they need the resources. So I think we are not collectively assuming our responsibility. Now, the most pressing needs. The main need, I think, is to feed, presently, is to feed supervised deep learning. I make 3 points about that. The first point is supervised deep learning depends on annotated data. I think everybody will be okay with that notion. Labeled data is required, and deep learning requires even more, even bigger data than previous techniques of machine learning, and new data is required to scale up. I know there is supervision, the trend of weak supervision, but in any case, this requires human labeled data at some stage. So there is a need for annotating training data. And by the way, this problem of annotating training data is exactly the same problem as the initial task to be automated by a neural net. Just that the exception that it's on a finite data set. But it's the same problem. Second point, annotation depends on automated pre-annotation because it's repetitive. For example, imagine the task of labeling queries to a virtual assistant, queries requiring tasks on demand. For example, here a small sample of data for a virtual assistant. It's about banking. So one of the queries is help me canceling my order. So why is it repetitive? Because there are recurrent situations and they need to be annotated each time they occur. For example, here the colors mean the labels to be assigned to the queries. And of course, there are frequent labels and less frequent labels. Here, the proportions are on the complete data, not on this small sample. And as usual, as often for natural sets of comparable items, like people in society or words in the text, there is some Zipf's law. That means that a small number of items will occur very often and a large number of them will occur rarely or just once. So this is why it's so repetitive. A large part is so repetitive and human annotators will get bored and make errors. So this misuse of human labor. And there is always the possible resort to crowd workers and undergraduates, which is very frequent, but I think it's not a reasonable solution to resort to inexperienced workforce, since the problem is more than when annotation is difficult. Otherwise, there can be other solutions, easier to automate. So a reasonable solution is more automated pre-annotation followed by human revision. My third point will be that this pre-annotation will depend on symbolic resources. The other solution would be to train neural nets to be able to pre-annotate the data required to train neural nets. I think it's somewhat ingenious to believe in this, at least for the moment, because obviously some bootstrapping in the beginning would be required. So again, a reasonable approach to this problem would be using people for human generalization and formalization of observations on raw data. And this frequent framework is called the neural symbolic to neural model in the typology of hybrid systems of counts. So it's classical. So what does that mean? That means rules and dictionaries. Here you have an example of rule in the form of lexicosyntactic pattern. These are the variants of French translation of "turn on the light in the hallway," in the idea that requests for a task-on-demand virtual assistant would have to be labeled. So these variants would get the same label. So it's in the form, the rules in the form of a finite automaton. And here a testimony about the use of dictionary. This is from a study that concluded that it works. Also, in addition to pre-annotation, some techniques of data augmentation also involve symbolic resources. To sum up, feeding supervised deep learning currently, in some sense, requires something like using symbolic resources. So, summing up the preceding slides, the simple model of we have annotated data, we apply deep learning, and we obtained a trained neural model needs feeding the annotated data. And this needs pre-annotated data revised by humans, and pre-annotated data needs a pre-annotation of raw data. So revision is already a human task, and pre-annotation in many cases requires symbolic resources which are made from raw data, which are not necessarily the same raw data that will be annotated. It can be larger, but raw data which are studied through a process of observation, generalization, and formalization by humans. And the same for data augmentation. And in addition, with this scheme, we have a bonus, which is human control on symbolic resources. We have direct control on symbolic resources since they are built by humans. We have a control on the knowledge encoded in the symbolic resources, on the definition and implementation of annotation guidelines, and indirectly, this provides human control on performance of hybrid systems through the impact of the data on training data and on trained models. So we have a method for quality improvement. Whenever we identify errors in a trained model, if we can trace the errors to a readable symbolic resource like a dictionary or a rule, we can fix the resource, rerun the pre-annotation, revise the data, and retrain the model, which involves human labor, but less than the initial labor. By the way, for the future, perhaps we can imagine improvements of this step of rerun the pre-annotation, taking into account the already annotated data. But I will not enter into this for lack of time. And this method of quality improvement is in fact the only method we know. Apart from that, if we have a trained model, we don't know what to do about it if it comes up with the wrong answers. So updating the preceding chart, we can add the feedback from annotated data and the performance of the trained neural model to the symbolic resources. And this creates a feedback loop, which is the basis for an iterative process of evolution of the system. In addition to this, we have another important, I think, contribution of symbolic resources, which is about, and which is also for tasks that can be automated without annotated data. Like tasks where training data is raw text, like translation. The only new information added to raw text is the alignment, and also word prediction or next sentence prediction. All these tasks are not really solved with supervised learning, but require at least tokenization. So tokenization, a small component with a strong impact on output. And for English and French, tokens can be space-delimited words, which is not so difficult to do, like in the example, 5 words, 5 tokens. But there are many languages with more restricted graphical delimitations, like Arabic. Small example in Arabic. Here, a word meaning "and he studied." In this word, the limit between the conjunction "and" the verb is not graphically delimited. There is no space here. And similar facts with agglutinative languages like Japanese, Korean, Turkish, Finnish, Hungarian, really many languages in the world. And similar facts with Chinese with no graphical delimitation, Vietnamese where only syllables are graphically delimited, which means that the limit between a word and the next is not more delimited than the syllables inside a word, which means that many meaningful units are not words, but subwords or something different than what is graphically delimited. And this, like here in the example in Arabic, one word will give 2 tokens, perhaps 3 tokens in the next slide. So in these many languages, the lexicon of words is bigger than the lexicon of meaningful units, and tokenizing into words instead of into meaningful units will produce data scarcity, because you need more data to cover the lexicon of words than to cover the lexicon of subwords. A lot of remarkable work has been done recently on this topic of relaxing synchronicity constraints in tokenization, so that now it's possible to have tokens that are subwords, tokens that contain spaces, like words in Vietnamese with several syllables, graphical delimitation inside the word, or even in English, multi-word expressions like on time, which it is interesting to consider as a single unit. And also, there are ways to obtain non-concatenative tokens, like in Semitic languages, pattern and root. If we go back to the preceding example, Yadruso, if I try to, I don't speak Arabic. The same example can be analyzed a little more into 3 tokens instead of 3, in spite of the lack of graphical delimitation. Here the verb has been divided into 2 parts: the pattern, which is the thing in black and red, and the root, which are these 3 consonants. And the rule is that the spots, the numbers for the spots in the pattern are replaced by the consonants in the root. And it's interesting to do that because the pattern and the root will convey different information. The verb, the information on the verb for the root, and grammatical information for the pattern. Here, active, imperfect, third person, masculine, singular, indicative. To do that, to do all of that, perhaps not all of that, because I don't think you have already non-concatenative tokens with neural tokenization, but at least you have the first 2. In this technique of neural tokenization, token limits are learned from combinatorial statistics in raw data, which means it's completely automated. But there's also hybrid tokenization, where dictionaries and rules are used to define possible delimitations. But there can be several possible delimitations due to ambiguities. So a supervised model chooses a best path among a lattice of possible delimitations. One of the earliest studies on this, I think the earliest study I have found is from SAC on Turkish. And this is not deep learning, but neural models in deep learning are also applicable to lattices, just like to sequences. So 2 advantages of hybrid tokenization. With this approach, the resources can take into account the semantic contribution of tokens. What do I mean by semantic contribution? An example in French: peuvent, can, pouvait, could. The difference in grammatical tense is more in the suffix, so the difference in the root does not correlate with any difference in meaning. So we can merge these 2 forms. There are different forms, but semantically they can be analyzed at the same item, if we take into account semantic contribution. And we have the reverse. In English, the 2 fulls of hopeful, that feels hope, and awful, which does not mean that feels awe, they are the same form, but it's better to analyze them as different items. So this can be encoded in dictionaries and rules. And this is an advantage as compared to neural tokenization that cannot take into account this meaning differences or non-differences. And also, the hybrid tokenization can manage non-concatenative tokens, which is not yet proved with neural tokenization, I think. As often, this approach is not mentioned in this recent survey because it uses symbolic resources, probably. And as usual, if you use it, you have bonus, which is human control on the definition of elementary units. So you can correct errors. So to sum up, symbolic resources are still useful in automating a large range of tasks with or without supervised learning. Now, this does not resolve everything. There is another problem. If you are not familiar with this world of symbolic resources, how can you spot good quality resources? So what are good symbolic resources? If you read the literature, academic literature, you often get a sense that there are no good symbolic resources. So that people say that they have reasons not to develop them, they have reasons not to use them, and as a result, symbolic resources are under investigation. Here are statistics about the approaches to information extraction. You see the really small proportion of rule-based or hybrid approaches. I think this has not changed, or not in the direction of more symbolic resources. And unfortunately, this creates a vicious circle where distrust of symbolic resources creates lack of research, which creates ignorance, which creates mistrust. But I think this view that all symbolic resources are unreliable is a prejudice and a misconception. As we saw, there is no objective evidence to show that symbolic resources don't work. Even if it's widely considered obvious in the domain, our responsibility as scientists is to be beware of obviousness. By the way, for centuries it was obvious that fleas might be generated by dust, and that's what was called spontaneous generation. It's ridiculous now, but it's our duty to doubt practically everything and to think critically. Even so, we have to explain this distrust of symbolic resources. We can explain it. I think one of the reasons is the dramatic progress achieved by deep learning, but I think it's not the only reason. We have to investigate also into the weaknesses of research on symbolic resources. I can talk about that because I'm also a linguist. So I know what I talk about when I talk about weaknesses of linguists. So I have still some time to review 4 challenges to linguistics for natural language processing, which will be maintainability, challenges in observation, in creating rules, achieving a high coverage, and in modeling and discretization. So about maintainability, symbolic resources as one of their advantages that they can be edited and maintained is that they should be easy to edit and maintain. This because they can be human errors that can have to be corrected. Language evolves, tasks evolve, can be extended, or extend it to new requirements of quality. In fact, it's exactly like software source code. It can be, it's more maintainable if it's compact, simple, and clear. For compactness and simplicity, I will illustrate this with dictionaries of inflected forms. Here, a dictionary of Portuguese inflected forms. You see all the forms in red. This contains a lot of duplicate information. They come from the same verb. Compare this with the dictionary of lemmas, where this verb occurs only once. So the right symbolic resource is the dictionary of lemmas, and you need the program to generate the inflected forms. Now, to illustrate clarity, I will compare finite automata with regular expressions. Practically all textbooks introduce regular expressions as a form to express rules. Many systems of natural language processing offer functionality of regular expressions to express rules. Now, compare with the finite automaton. The finite automaton that I already showed, which contains variants of phrase. Theoretically, finite automata are equivalent to regular expressions, so I was able to create the equivalent regular expression to this automaton. What would you think if you had to correct an error or introduce an extension either on the automaton or on the regular expression? Take the point of view of the person that maintains the symbolic resource. Obviously, the automaton uses the 2 dimensions of the screen better than the regular expression, which is a formula in 1 dimension. So it's more readable in this way. But a few people know that. Even among linguists. In general, I can say that not all linguists address the challenge of maintainability, but some do, so it's interesting to check in their papers and in their resources. Now, another challenge is about observation. Dictionaries have the reputation of containing errors. Sometimes it's the case. For example, the word in a dictionary is cucurbitaceae, which is a family of plants. Many dictionaries of English and of French also, by the way, describe it as the plural noun, which has no singular, which is an error because there are attestations in the singular, as you can see here. It's an attestation from an encyclopedia. So this exists. To solve these problems of observation, or to investigate this problem of observation, we can enter into the question of what are the possible methods of observation for a language. There are two types of method. First is of authentic attestations. You find an attestation, just like here, the attestation in an encyclopedia. And for example, if we want to know if this construction, the lake missed its freeze date by 2 days, is in use or not in English. So one method, a reasonable method to find attestations. In the case, it will not be very successful because we find no Google hit, even for missed its freeze date, without the complement with the preposition by. And still a problem, absence of evidence is not evidence, which means that the fact that there is no Google hit does not mean it's not in use. because there may be a statistical reason why the sequence is not found. Perhaps it's a too long sequence of items which are not frequent enough. So it's not so easy to deduce something from a query for authentic attestations, but it's useful, of course. So here in the example, there is an attestation of something quite close, some lake mist. Its average ice out date of May 7. Ice out date will be the date when the lake has lost all its ice. So perhaps it was really in use. Now, due to these problems, we need another method, which is that of introspection, which is exploiting the competence of every native speaker to know if some form is in use in their native language, mother language. But this requires training, caution, and peer reviewing. Why? Because if you make a description with in your mind the idea that something is in use or is not in use, you may be judge and party and decide in favor of what you want to prove. But there are ways to avoid this problem, which are training, caution, and peer reviewing. So this presentation was just to show that these observation methods are maybe really tricky. And not all linguists are cautious about that, but you can check in their papers. Now, third challenge is that of rules, making rules and coverage. My starting point will be the fact that the proportion of chaos in no language is stunning. An example in Arabic, the broken plural. Here an example which shows broken plural. It uses the notion of pattern and root that I showed about the Arabic translation of "and he studied." To produce the plural of this Arabic word meaning tooth, you need to know the pattern of the singular of this word. The word is a combination of this pattern and root made of N, A, and B. So replacing the numbers with the consonants, you obtain NOD. And to make the plural, you need to identify the singular pattern, replace it with the plural pattern that you can see is quite different. And in that case, change a little bit one of the consonants in the root. So many words in Arabic follow these rules of producing plurals. There are not many singular patterns, a few tenths. There are not many plural patterns, and there are not many root alternations, but the combinations are many. And in this reference, you find statistics of 160 combinations of these two elements, which mean 160 algorithms of making broken plurals. And there are also the words that form their plural in another way. This is not specific to Arabic. We find chaos in any language, any natural language, because they are natural. And the important fact is that partial coverage will not help. Like describing broken plural only for triliteral roots. Triliteral roots are roots of this type with 3 consonants. If we describe broken plural only for these roots, what will happen if we happen to, with a root with 4 consonants occurs in the text? There are many roots with 4 consonants, and there are some with 2 or 5 consonants. So it does not help. I have no time for the other example. And practically any rule in natural languages has exceptions, and it will be impossible to find a correct rule without checking the whole lexicon. So finding rules involves really a big descriptive task. Here, sum up of the summary of the challenges of making rules. There are observational challenges, achieving high coverage, accuracy. The rules must be accurate they must be consistent with the use, and other observational challenges. There are modeling related challenges. To choose a model for that, comparing models of rules. For example, you can have rules that chain or don't chain. Chaining means the output of a rule is the input to the next rule, and have rules with a hierarchy of rules and exceptions or not. How can they be updatable? So this makes the problem interesting, and the human driving force to solve these problems is curiosity. But strangely, not all linguists accept the descriptive part of the task. I think the larger problem is that of coverage. Many linguists will not accept the descriptive part of the task, but fortunately, you can check in their papers and resources. Many will think that making the rules will be the noble task, and scanning the lexicon is a menial task, but they don't say who would do the job. Perhaps not the geeks. And I have no time for the fourth challenge, so I will skip to the conclusion. So here are the answers I tried to give to the questions. Pure neural nets is a bet on the future, of course, but is it a reasonable bet? Well, we don't know. We don't know about the future. But what if pure neural nets turn out not to be the best approach to all NLP tasks? Of course, we cannot rule out this possibility. So this means that if we all bet on the same strategy of pure neural nets for all applications, there is some risk that we don't assume our responsibility towards the domain. Now, another problem for NLP is, what will we use symbolic resources for? There are three uses: preparing data at less expense, guiding the evolution of systems, and handling the right elementary units in tokenization, which are interesting advantages now, and for the future, we don't know, but we don't know. And about the question of selecting good symbolic resources for NLP, I tried to give 4 criteria: maintainability, carefulness of observational processes, coverage, and if they follow a discrete model, I had no time about that. So taking into account all these facts, I think we can find a better synergy between machine learning and symbolic resources than what is happening presently. Thank you for listening.